So, we have looked at one quantum spin and how effectively measurement can destroy the state of the system. Now, let us look at a little more complicated issue, which is two quantum spins. So, consider two spins up and down, and they are in this state. So, the combined system or the combined state of the system is let us call it as say psi. It's equal to A up plus a B up down plus a C down up and a D down down. So, that is the most general state of the system, where A, B, C, D are complex unknown coefficients. So, we are actually talking about the Z basis, and in that basis A square is the probability that both spins are in up state and B mod square is the probability that first spin in up state and second in down state C mod square is the probability that first spin in down and second in up state, and finally, D mod square is the probability that both spins are in the down state. Clearly, the total probability has to be equal to 1. So, the A mod square plus B mod square plus C mod square plus D mod square will be equal to 1. Now, let us ask a few questions, relevant questions that to for quantum teleportation. So, what happens if we just measure the first spin? For up outcome for the first spin, the probability is A mod square plus B mod square. Similarly, for down outcome, the corresponding probability is C mod square plus D mod square. So, after the measurement, the state of the two spins corresponding to up outcome for the first spin is a divided by root over a square plus b square plus, so that is that corresponds to up and a plus b a square plus b square up down. So, that is after the measurement, this is the state of the system. We can call it as a state phi. Okay. So, this is the first spin is up and this corresponding to the second spin being up and down, and similarly for the, so this is let us call it as up, and similarly for the down outcome, phi down equal to c divided by root over c square plus d square, and then you have a down up plus a d divided by a c square plus d square down down. So, what it basically means is that if we measure the first spin in the up state, then we remove all terms in the superposition except the ones that preserve the first spin in the up state, and similarly the same goes for the down state. Then we remove all terms in the superposition where the first spin is in down state. Okay. And similarly for the first spin to be in the down state, we remove all combinations which yield that the first spin is in the up state. So, again if we go to that introduce the x basis, for one spin at a time, so the first spin, so this is corresponding to the first spin, we have up up which is equal to a 1 by root 2 a right down plus 1 by root 2 left up. So, this is for the first spin, and then this is the for the other one. So, these are the combinations that one can write down, and this is again this minus 1 sorry plus 1 by root 2 down and down here. And for the second spin, so these are the linear combination of the z basis in terms of the x basis for the first spin. And for the second spin, so we have up up, it is written as 1 by root 2 up plus 1 by root 2 up up left, and similarly for the down up. So, this is for the second spin being up. So, it is a 1 by root 2, a down and a plus 1 by root 2 and so on. Okay. So, these are the linear combinations for the spins to be written in the z basis in terms of the x basis. Let us now write down the most familiar state that we are aware of for a two spin system or a system consisting of two spins, namely the singlet state. This you have seen it. Okay, so, let us write down a singlet state. So, this is the singlet state which you are aware of, 1 by root 2 up down minus a down up. The important thing now, which we have not said earlier, we have of course discussed it in the context of what kind of states or what are the different states that can take place in the context of this for a system of two spins. The singlet is just one and there are three triplet states that also come. The singlet state is actually antisymmetric with respect to the change in the spins. But what is most important for us here is that it is an entangled state of two spins. The properties are if either spin is measured along any axis. In this particular case, any axis means the plus z axis or the minus z axis, that is in the up state or in the down state, any axis, the outcome will always yield up with 50% probability and down with 50% probability. Okay. So, this is a property of this singlet state and it is important for us. And it is also important to note that if we measure one spin along any axis the result for the other spin is always anticorrelated. So, what it means is that if one of them is found in the up state, the other is always in the down state and vice versa. So, this is what you see in this particular case, that one is in the up state and the other is in the down state, and so this is in the down state, the first one is in the down state and the other is in the up state. So, this is a property of that state, singlet state. Okay, so, they are always anticorrelated. So, basically this means that knowing the state of one spin So, we automatically know the result that would yield other spin. Okay. Let us just give you an example that if you ask your friend to draw an up arrow on a piece of paper, a big up arrow, and take a Xerox of it by reversing the page, that is rotating the page by sort of 180 degree, then you know that up will become down. So, if you know that the friend has drawn an up arrow, the result of the outcome after a Xerox is taken with the page being rotated by 180 degree, you know that the result is going to be a down spin. So, it is that kind of a situation that we are talking about. But you see, the important thing is that all these measurements, just now also what we have said, that the measurements actually destroy the states. But there are other kinds of measurement which do not destroy the states, and these are called as unitary operations or unitary measurements. Let us see them. Because we did not want to destroy the state for the reason that as was discussed in the last discussion or deliberation that we have been conducting, once you do a measurement, all these entangled states are gone, and once you have this depletion of these resources of entangled states, you cannot do a teleportation. So, it is very important for us to understand that what operations would not actually destroy the states, and these are the unitary operations. So, we have so let us just write that so far we have seen that measurement yield information about the state but also have the consequence of destroying the state. Destroying the state, what we want to say is that the remaining bit of information, as just if you look at it here, that we have measured the up spin in the first spin in the up state, which means that there are no C and D coefficients, because there the spins were in the down state. And similarly, when you have measured the first spin in the down state, there are no information about A and B coefficients, because which correspond to the amplitudes for the first spin to be in the up state. So, we are talking about that. So, destroying the state means the remaining information. So, let us just make it more clear. So, there is another class of operations, as I said earlier, which reveals nothing about the state and hence does not destroy anything. These are called as unitary operations. And of course, the most familiar unitary operation for you is a rotation. So, what we mean by that is that if you rotate an upspin about z axis by about x axis by pi, we would get up will go to down. However, for this will remain invariant. So, if we come back to the language of quantum teleportation, then and call this rotation by pi about the x axis as x operation. So, this you define as the x operation or it is also called as the x gate. Then x gate acting on the unknown single spin state So, then x on A up plus B down, and the reason we call it an unknown state is that these A's and B's are unknown, these are unknown amplitudes or unknown coefficients. This will become A down and will become B up. So, it does not destroy any information and you can also see that if I do it twice, then it will come back to its original state. All right. So, so this is about the X gate operation. So, X gate operation simply reverses the up to down and the down to up and without changing anything, and if you do it once, so that is x square acting on that would get back the state that we had seen. Now, define, so this is 1, then define rotation about z axis as z operation basically by, so this is by pi by an angle pi and this is also by an angle pi. So, this is called as a Z operation or it is also called as a Z gate. So, a Z gate acting on this unknown spin state is given by this. It is equal to A up minus B down. You have to convince yourself that why there is a minus sign coming. For that, if you look at the rotation operator written in terms of an exponential, so which is basically it goes as exponential I theta and the n cap dot s, that is the rotation operator for a spin, and here theta is equal to pi, and because it is above the z axis, and so it will the sz or the sigma z will come, and since the sigma z has in the up and down basis written, there are the two diagonal elements have a relative sign difference. That sign difference is appearing here. So, let me write down that the negative sign before the second term is due to the relative sign difference of elements of sigma z written in the up and down basis. Just to remind you that sigma z is equal to 1 0 0 minus 1. Okay. So, that is the x and z operations that you can see. Let me just make a block of this. This is the x operation. This is an important ingredient to the quantum teleportation. So, we will write this, and this is a z operation. So, these are important. We are going to only define another operation which is called as the constrained x operation. So, we will call it a Cx 3. Define a controlled x operation. The word control will just make it clear, which is abbreviated as again by a rotation pi Cx gate, which yields the composite state of two spins. Let me first write down the relation and then we will explain. Two spins. So, this is Cx acting on A up plus B up down plus a C down up plus a D down down. This will yield a up plus a B up down plus a C down down plus a D down up. So, what it does is that it looks at the first spin, that is the one on the left inside the ket, and sees if it is up then it does not do anything, and if it is down then it flips the other spin. Okay. So, in these two terms here, the up spin, the first spin is in the up state. So, it does not do anything. In the next two terms, the first spin is in the down state. So, it flips the other spin, makes it down here and makes it up here. So, this is called as a constrained x operation. Cx looks at the first spin so if it is up does nothing. If it is down, flips the next spin, flips the second spin. Okay. So, just to remind you that these are the three operations that we need for quantum teleportation of a spin. Let me also do a box of this operation. So, these three operations are needed in order to understand. Okay. So, let us just okay. So, we take an unknown state 1, take an unknown state psi equal to A up plus B down. This state is in lab A, and the final goal of the teleportation is to transfer it to lab B. Second is that take a singlet state, which is an entangled state in our language now, singlet, or we call it entangled state. In fact, so this is important for us now, which let us write it as psi s, s for singlet, it is 1 by root 2 up down minus down up. Okay. Now, remember that we call this as spin 1. So, this is called as spin 1, and so spin 1 is in lab A. This one is called as spin 2, and this one is called as spin 3. So, spin 2 is in lab A again, and importantly spin 3 is in lab B. Okay. So, these are the important requirements. Now, how an entangled state, one is in lab A and one is in lab B, is what we have seen in the last discussion, in which they have physically met at some point in the past, and they have created a lot of entangled state and they have carried it to their respective locations. That is the only justification that we can give for this entangled state to have one spin in lab A and lab B. And remember, lab A and lab B are physically either very far apart, or they are by some impenetrable wall, they are separated by. So, with this we start our work. So, we will write down the composite state of the system. So, which is the composite state be phi, which is equal to A by root 2 up down minus B by root 2 2 down, up, down minus a by root 2 up, down, up plus b by root 2 down, down, up. These are basically obtained by multiplying the amplitudes. Okay. So, the first one if you consider, so it is a up and now it is getting multiplied with 1 by root 2 up, down. So, that is how the first term came. So, this is equal to a by root 2 and we have simply taken it as up, up, down. That is the first term. That is the first term here. Okay. So, this term is written as this and again. So, all these other terms can also be similarly justified. Okay. So, once we have that, let us just write down the flow chart for quantum teleportation. So, there are essentially 5 steps that will follow with the help of the gates which are X gate, Z gate and Cx gate, and will achieve the teleportation of the unknown spin from lab A to lab B without really making it travel from lab A to lab B, and anyway it is not a possible journey that we have talked about earlier. So, step 1, this step 1. So, apply Cx operation on phi. Okay. So, Cx on phi on this a by root 2 up, down minus b by root 2 down, up, down, down minus a by root 2 up, down, up plus b by root 2 down, down, up. Remember, the rule is that if it says the first spin is still the leftmost one inside the ket. If it sees the first spin in up state, it will do nothing. If it sees it in down state, the down state, then it will flip spin 2. So, this is equal to a by root 2 up, up, down minus b by root 2 down, down, down minus a by root 2 up, down, up plus b by root 2 down, 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 up, up. So, that is the operation that Cx gives. So, step 2 is now measure spin 2 in the Z basis. So, probability of getting up for spin 2 is, so it is that curtailed information that we get. We have a by root 2 mod square plus a b by root 2 mod square, which is equal to a mod square plus b mod square by 2, which is equal to half. So, same for down spin for spin 2. So, basically we get %, for each outcome. Okay. So, that is step number 2. Let us assume that we got a up outcome for spin 2, then the state is equal to a by root 2 up down plus a b by root 2 down up. Okay. The rest of the information is gone, as we have noticed earlier. So, this is the state after this for up outcome for spin 2, and similarly it will be same for the spin 2. Sorry. Similarly, is this it will come out to be same for the down as well. So, that is your state, and now we will go to step 3. We will writing it not in Roman. So, we will follow that same. So, now measure the first spin in the x basis. Okay. So, the resulting state from up down plus a b by root 2 up down up, it became a by 1 by root 2 right up down plus 1 by root 2 left up down plus b 1 by root 2 up plus minus 1 by root 2. This will be minus, check this, this is up. Okay. So, again after step 3, the right outcome with 50% probability and a left outcome also with 50% probability. Okay. So, the state becomes if you want to do it, measure it in the right state or in the left state, it becomes equal to a by root 2 up in the right state. So, for right outcome for spin 1. Once again, just to remind you, spin 1 and spin 2 are in lab 1 and spin 3 is in lab 2. So, this would be this plus b by root 2 up right up. So, that is the outcome. So, now let us go to step 4. Lab A communicates the results to lab B. Okay. So, all the results so far, that is getting the right state for spin 1, etc. So, this state is essentially communicated to lab B, this state that we have obtained here. The state that we have obtained here is communicated to lab B. So, step 5 is a little involved. So, the following, so in lab B, after they get all these outcomes, if the measurement outcomes were number 1 for spin right for spin 1, spin that is labeled as 1, and down for spin 2, then do nothing. If it is left for spin 1 and down for spin 2, apply Z gate to spin 3. Remember, all these gates actually rotate by pi. So, that is it is not specified all the time, but that is what it means. Right state for spin 1 and up state for spin 2, then apply X gate to spin 3. Finally, if it is a left for spin 1, basically all combinations of right and left and up and down for 1 and 2. And this is down for this is going to be up, because we have taken the down already. This is going to be up for 2, then well, it should be written a little below. For a left for 1 and up for 2, then apply successively X Z gate and then X gate, Z gate and then X gate to spin 3. Okay. So, if you look at our case, the lab whatever has been the final state so far, which is here given by this state. So, we have the first spin to be in the right state and the second spin to be in the up state. So, we basically should apply 3. So, it is right and up. So, we will apply the x gate to spin 3. So, that is the conclusion from this, and this is exactly what we will do. So, for us 3 is applicable. And that so which means that perform x gate to spin 3, that is what is written, apply x gate to spin 3. This yields a by root 2 up, up, up. So, if it sees the first spin in the right state, then then it will not do anything. So, basically if it sees the second spin in the up state, then it will not do anything, but if it sees the second the third one, so this will be equal to so this is so we have the first spin. So, we have a by root 2 and right up, up. So, this is going to give that it is going to flip the spin for this third one, and it is going to flip the spin. If it is in the up state, then it will flip the spin for the third one to be in the down. So, this will be like this. So, it is a up, up plus a b by root 2 and up, up, down. So, this says that the state for the two spins in lab A is lab A is up, right up, that is this right up, and for lab B is A up and a B down. This is essentially the unknown state. That we started with. Which was initially in lab A. Now, it has come to lab B, it has been teleported to lab B. Now, whether such a simple operation or a series of operations that is applied to a single spin or entangled state would hold for humans, that is a question. There is a lot of debate and disagreement that humans cannot be teleported, for the simple reason that there are nearly 10 to the power maybe 30 or 10 to the power even more than that number of atoms which have their positions and their momenta etc., all degrees of freedom, and transporting a single spin from lab A to lab B may be achievable, but so many degrees of freedom, each one will have to be transported or teleported, whether that remains a possibility needs to be checked. In fact, it is very even seriously optimistic people will also oppose that such a thing can ever be achieved. So, this is simple demonstration of quantum teleportation that we can achieve for a single spin in the unknown state in a lab. We had talked about a spin half particle, but in principle it can be sort of extended to higher spins and so on.